In this section, we're going to talk about a result called Bayes' theorem. And I think what we're going to do first here is we're going to state it, prove it, and use it. And then I'll talk about why this is an important result. So let's start with the statement of Bayes' theorem. This is Bayes' theorem. For events A and B, and because we've got conditioning going on, we need them to be greater than 0, we have this expression here, which is that the probability of A given B is the probability of A times the probability of B given A, that's the other way round, divided by the probability of B. So this here is Bayes' theorem. Before we go any further, let's prove it. The key here is to look at the probability of A intersection B, because this can be written as two different ways using the ideas we've seen in this section about conditional probability. One way is we can condition on B, to write it as probability of B, probability A given B. And the other way we can do it is we can condition on A to get probability of A equals probability B given A. So those are two different ways of writing the same thing, where that same thing is the probability of A and B. And so because we've written probability of A and B in two different ways, well, those two things must be equal, right? It must be the case. Probability of A, probability B given A is equal to probability of B, probability of A given B, because they're both equal, probability of A given B. And if we divide both sides by the probability of B there, right? We divide both sides by the probability of B, we get Bayes' theorem. So that's an easy enough proof. We just wrote probability of A and B in two different ways. Now let's see if one way we can use Bayes' theorem. And we're slightly going back here to an example. It's a bit similar to an example we had earlier. So my friend is picking his 4, 6, or 10-sided dice, equally likely. But he does it in secret and then tells me he's rolled a 5. What's the probability he picked the 6-sided dice? So if we think what this question is asking for, it's asking for the probability of the 6-sided dice. Remember that we use the notation D6 for that. Given he rolled a 5. Well, what we can do is we can use Bayes' theorem to rewrite this. So you'll remember that if we write this in terms of Bayes' theorem, it becomes probability of D6, probability of roll 5 given D6 over probability of roll 5. And this is good news, actually, because we know what all three of the numbers in this expression are. First, probability of D6. Well, we know that all the dice are equally likely, so that's 1/3. Probability that we roll a 5, given it was the D6. So given that he chose the 6-sided dice, what's the probability he rolled a 5? Well, that's 1 in 6, right? Because there are 6 possibilities on the dice, and one of them is a 5. What's the probability of rolling a 5? Now, you might remember we proved that in the last subsection using the law of total probability. So if you go back and have a look, you'll see that when we used the law of total probability, we saw that the probability of rolling a 5 was 8/90ths. And if you cancel out all the fractions there, the 90 goes onto the top, the 3 times 6 times 8 goes down to the bottom. I think this all works out to be 5/8ths. So 5/8ths is the probability our friend chose the 6-sided dice, given he rolled a 5. Okay, so now I want to talk about why Bayes' theorem is important. And there's two reasons, I think, why Bayes' rule is important. The first thing is that if we look at it here, it's telling us about a relationship between the probability of A given B here and the probability of B given A here. So the first thing is, it's very important not to confuse the probability of A given B with the probability of B given A. Right, those are two different things. The example I use in the notes is I say that the probability of someone being under the age of 40, given they're a Premiership footballer, is very large, because almost all of the Premiership footballers are under 40, so that's very large. But the probability that someone is a Premiership footballer given they're under 40 is small, because there are lots of under 40 people and only a few of them are Premiership footballers. So you've got to remember that PA given B and PB given A are different. But Bayes' theorem tells us how to relate them. If you've got PB given A, if you multiply it by probability of A over probability of B, you get probability of A given B. So in this view, Bayes' theorem is sort of a technical result that helps us when we have the conditioning the opposite way around from what we want. If we've got probability B given A, but we want probability A given B, then we've got Bayes' theorem as a tool in our toolbox to help us solve it. And you can see that's kind of what we did on our example here, which is that we wanted the probability of D6 given roll of 5, but we knew probability roll of 5 given D6. Probability roll of 5 given D6 is dead easy. It's a sixth, because there are only 6 possibilities on the dice and one of them is a 5. So we kind of wanted the conditional probability the other way round from the easy one, and Bayes' theorem allowed us to switch it round. That's one reason why Bayes' rule is an important rule. It's kind of a technical tool to allow us to swap over conditioning. Second way to think about Bayes' rule and why it's important is it tells us how to update our beliefs when we see new evidence. For example, let's say we're thinking about some event A. We think that the probability this event A will happen is probability of A. But then we see some new evidence, and this new evidence is that B happens. So now we should update our belief that A will happen based on this new evidence. And we want to update it to A given B, as in what's this new updated probability given the evidence we've seen. And so we can also interpret that in terms of Bayes' theorem. Right, so we started by thinking the chance A would happen was probability of A. But then, when we saw B happen, we wanted to update our estimate of the probability to the probability of A given B. We wanted to update. And Bayes' theorem tells us how to update. We have to multiply by PB given A and divide by P of B. So in that view, Bayes' theorem is telling us how to update our beliefs. This becomes very important in a type of statistics called Bayesian statistics, where you start off by saying how likely you think a scientific hypothesis is, then you collect some data and you update your belief about the scientific hypothesis. We'll be seeing that in week 10 of this course. Right at the end of the course, we'll talk a bit more about this second interpretation of Bayes' formula in terms of updating our beliefs. There's one other thing I want to say, which is that we've seen two big results in this section. We've seen the law of total probability and we've seen Bayes' theorem. And it turns out that quite often we want to use the law of total probability and Bayes' theorem together, which is like this. Suppose we have a partition A1, A2 up to AN. You could perhaps think of these as dueling scientific hypotheses or something. And Bayes' theorem tells us the probability of AI given B. You'll know this by now. It's probability of AI, probability B given AI, over probability of B. But also we can expand out that probability B at the bottom using the law of total probability, because we have a partition. Right. The thing on the bottom is the sum over all the partitions, the probability of that partition, and the probability of B given that partition. Then the top is still the same. So that's combining Bayes' theorem and the law of total probability in a way that's often useful. In fact, if you think about what we did with the dice problem, in the last subsection, we used the law of total probability, And then in this section, we used Bayes' theorem and used that previous result. So we kind of did use them both, but we did it in two separate steps. Whereas in the equation I've just written down, I'm writing it down in just a single step. It's kind of a matter of personal taste, which one you prefer. But it is important to know that like Bayes' theorem and the law of total probability fit together very nicely. And often the techniques we want to use both. And in fact, in the next subsection, we will see a famous example of how we can use Bayes' theorem and the law of total probability together.